Chapter 12 concludes with a short section on catalysis. So as we know, catalysts are species that speed up a chemical reaction but are not consumed in the course of the chemical reaction. And how catalysts function is they provide an alternative reaction pathway that has lower energy of activation than the uncatalyzed reaction. So a very famous example of catalysis is the degradation of ozone, O3, in the upper atmosphere by chlorofluorocarbons. So what tends to happen is for most of the year above the southern pole, there's fairly constant concentrations of ozone in the stratosphere. But just before summer in the springtime, there's this big dip in ozone concentration right above the southern pole. And this causes what we call the hole in the ozone layer. And this hole was getting bigger and bigger and bigger and spreading to latitudes further and further north every year. And it was kind of a mystery as to why this was occurring. And then chemists figured out that it was a result of the catalytic action of a class of compounds called chlorofluorocarbons, or CFCs. So the natural decomposition of ozone occurs via a two-step mechanism. The first step is fast, it's not the rate determining step, and in this step it's unimolecular. One molecule of ozone decomposes to form a molecule of O2 and atomic oxygen. In the second step, which is the rate determining step, it's the slow step, a molecule of ozone reacts with the atomic oxygen produced in the first step to form two molecules of O2. So overall, the reaction is that two molecules of ozone decompose to form three molecules of O2. When we work through and figure out the rate law for this reaction, we see that it is first order in O3, and we can determine that it has an activation energy of 17.7 kilojoules per mole. Now, one of the more common CFCs is trichlorofluoromethane, and it's very commonly used, or until recently was very commonly used as a refrigerant. Its production was banned in the US in the mid-90s. And these compounds were designed to be really inert. And what that meant was that they wouldn't kind of make your food taste funny, they were non-toxic, they weren't harmful to health, they were very, very chemically stable. Now there is a problem with this. Things that are chemically stable are not going to decompose very quickly, and as a result, this particular CFC would make it all the way to the top of the atmosphere chemically unaltered. When it got to the top of the atmosphere, what we call the stratosphere, the concentration of UV radiation up there is very, very high, and then we start to break bonds within this stable molecule. And what happens is we end up with atomic chlorine. And atomic chlorine is an example of a species that we call a free radical. It has one unpaired electron, and it's very, very reactive. Now, it turns out that chlorine atoms, monatomic chlorine, catalyzes the breakdown of ozone. So in the catalyzed breakdown of ozone, an atom of chlorine reacts with an ozone molecule to form a molecule of ClO and a molecule of O2. In the second step, what happens is a molecule of ClO reacts with a molecule of ozone to regenerate the chlorine, and it makes two molecules of O2. So you add all of this together, and what you realize is that the chlorine doesn't get consumed. And so we have the chlorine just goes around and around and around. So the chlorine atoms that are consumed in step 1 are reformed in step 2, so they don't get used up. So one chlorine atom is just going to keep going around and around and around in this reaction and never get exhausted. Now there's another problem as well. The energy of the activation energy for the decomposition of O3 in the presence of chlorine is a lot smaller than the normal process. And we have to remember that there's an exponential dependence of the rate on the energy of activation. So here's our uncatalyzed conventional process in the absence of chlorine with its energy of activation 17.7 kilojoules per mole. And here's our catalyzed process in the presence of chlorine. It's going to go a lot quicker. And so that one chlorine atom is just going to go keep around and around and around and around until the chlorine gets lost, or perhaps it reacts with something other than ozone and kind of gets taken out of the system. So that's a problem. We banned the use of CFCs and we're on track now to eliminate the ozone hole. And it's kind of a cool story because chemists saved the world. We were literally heading for Armageddon. Chemists figured out what was going on. A fairly small change was made, and now everybody gets on with their lives. So this is sort of a classic example of catalysis. So the chlorine atoms produced by the photolysis or the photo breakdown of CFCs are a classic example of homogeneous catalysis, where the catalyst and the things that they are reacting with are in the same phase. So another good example of homogeneous catalysts are enzymes. Enzymes are proteins that catalyze reactions, and they're going to be in the same phase as the reactants that they are interacting with. So you're probably familiar with some enzymes being used as catalyst. They are often in laundry detergents. So laundry detergents might have a lipase, which helps dissolve lipids or fatty things, and then they might have a protease, which helps dissolve protein dirt. Perhaps you've heard of pineapple enzyme. Pineapple enzyme is often present in facial cleansers because it kind of just tends to sort of like, it has an effect of sort of like breaking down tough proteins, to be honest. And it's also pineapple enzyme that's in meat tenderizers for the same reason. So these things are, scarily close in composition. Heterogeneous catalysts are different. In a heterogeneous catalyst, the catalyst and the reactants are in a different phase. And that can be, very, very beneficial because it means that you don't have difficulty in keeping or in recovering your catalyst from your reaction system. So a good example of this is the catalytic converter that's in your car. The catalyst that's in your car is a solid. It's generally a solid that is coated onto sort of like a honeycomb-like matrix to maximize surface area. And then what it's reacting with is actually gases. So the gases passed over the solid catalyst, and you can see that it's actually kind of convenient because, if we had a gaseous catalyst, well, our catalyst would just get blown out the exhaust pipe. But by keeping it as a solid, it's easy to separate the two components, and it prevents our catalyst from getting lost. The catalytic converter that's in your tailpipe does a really cool reaction with NO. It takes NO and it catalyzes the reaction back into N2 and O2, which obviously are harmless gases that are naturally present in the atmosphere, whereas NO is a major component in acid rain and what's referred to as phytochemical smog. This is the thing that gives the brown haze over cities on a smoggy day. So how do they function? How do they work? Well, one of the ways that is very common for a catalyst to work is that it'll hang on to one or perhaps even both of the reactants, and it'll keep them in a favorable orientation. And that just increases the likelihood of there being a successful collision. So the catalyst that's in your car, for example, binds NO, and it makes the NO molecules line up in a way that holds them, that is favorable for reaction. So that's a kind of a classic example of how a catalyst might work. Some enzymes do the same thing. They hang on to one of the reactant components and present it in a favorable orientation for the other one.